Welcome to a video lecture on Introduction to Atomic Structure. I'm Dr. Jinesh. I'm from Department of Chemistry, Ramaya University of Applied Sciences. After this session, you will be able to define inorganic chemistry, understand the basics of formation of elements, and list major milestones in atomic structure. What is inorganic chemistry? If organic chemistry is defined as the chemistry of hydrocarbon compounds and their derivatives, inorganic chemistry can be described broadly as the chemistry of everything else. This includes all the remaining elements in the periodic table, as well as carbon, which plays a major and growing role in inorganic chemistry. The large field of organometallic chemistry bridges both areas by considering compounds containing metal carbon bonds. It also includes catalysis of many organic reactions. Bioinorganic chemistry bridges biochemistry and inorganic chemistry and has an important focus on medical applications. Also, environmental chemistry includes the study of both inorganic and organic compounds. We will go into a little bit history of inorganic chemistry. Even before alchemy became a subject of study, many chemical reactions were used and their products applied to daily life. The first metal used was probably gold, which can be found in metallic state in nature. Copper can also be readily formed by the reduction of malachite, which is a basic copper carbonate, in charcoal fires. Silver, tin, antimony, and lead were also known as early as 3000 BCE. Iron appeared in classical Greece and in other areas and the Mediterranean Sea by 1500 BC. At about the same time, colored glass and ceramic glazes were introduced, largely composed of silicon dioxide, that is, silicon dioxide is the major component of sand, and other metallic oxides, which had been melted and allowed to cool to amorphous solids. Alchemists were active in China, Egypt, and other centers of civilization early in the first centuries of CE. Although much effort went into attempts to transmute base metals into gold, alchemists also described many other chemical reactions and operations. Distillation, sublimation, crystallization, and other techniques were developed and used in their studies. Because of the political and social changes of the time, alchemy shifted into Arab world and later about 1000 to 1500 CE reappeared in Europe. Gunpowder was used in China. Chinese fireworks as early as 1150. And alchemy was also widespread in China and India at that time. Alchemists appeared in art, literature, and science until at least 1600, by which time chemistry was beginning to take shape as science. Roger Bacon, 1214 to 1294, recognized as one of the first great experimental scientists, also wrote extensively about alchemy. By the 17th century, the common strong acids, nitric, sulfuric, and hydrochloric acid, were known, and systematic description of common salts and their reactions were being accumulated. As experimental techniques improved, the quantitative study of chemical reactions and the properties of gases became more common. Atomic and molecular weights were determined more accurately, and the groundwork was laid for what later became the periodic table of elements. By 1869, the concepts of atoms and molecules were well established, and it was possible for Mendeleev and Mayer to propose different forms of the periodic table. The chemical industry, which has been in existence since very early time in the form of factories for purifying salts and for smelting and refining of metals, expanded as methods for preparing relatively pure material became common. In 1869, Becquerel discovered radioactivity, and another area of study was opened. Studies of subatomic particles, spectra, and electricity led to the atomic theory of Niels Bohr in 1930, which was soon modified by the quantum mechanics of Schrödinger and Heisenberg in 1926 and 1927. We'll study about Big Bang theory and origin of atoms. Scientists observe that the universe is expanding. 15 million years ago, the currently visible universe was concentrated into a point-like region called singularity. Then Big Bang was happened. With initial temperature immediately after the Big Bang was about 10 to the power 9 Kelvin. The fundamental particles produced in this explosion had too much kinetic energy to bind together in the form we know today. However, the universe cooled as it expanded, the particles moved more slowly, and they soon began to adhere together under the influence of a variety of forces. In particular, the strong force, a short-range but powerful attractive force between nucleons. Nucleons means protons and neutrons, bound these particles together into nuclei. As the temperature fell still further, the electromagnetic force, a relatively weak but long-range force between electric charges, bound electrons to nuclei to form atoms, and the universe acquired the potential for complex chemistry and the existence of life. How elements were originated. About 2 hours after the start of the universe, the temperature had fallen so much that the most of the matter was in the form of hydrogen atom, 89%, and helium atom, 11%. In one sense, not much has happened since then, for still hydrogen and helium remains overwhelmingly the most abundant element in the universe. However, nuclear reactions have formed a wide assortment of other elements and have immeasurably enriched and variety of matter in the universe, and thus given rise to the whole area of chemistry. The light elements were formed by nuclear reaction in stars, formed the primeval hydrogen and helium. Heavier nuclides are formed by the processes that include neutron capture and subsequent beta decay. Properties of subatomic particles. Atomic number Z is the number of protons in the nucleus of an atom. Atomic mass or mass number or nucleon number, normally represented using the letter A, is the total number of protons and neutrons in the nucleus. Isotopes, atoms with the same atomic number but different atomic masses. Some elements have different isotopes with the different atomic masses. So to calculate the average atomic mass, the percentage and atomic masses of different isotopes to be considered. Therefore, atomic mass will have decimal places. Hydrogen has an atomic mass of 1.004 due to the existence of hydrogen isotopes with atomic masses of 2 and 3. These are some subatomic particles, symbol, their mass number, and charge. For example, electron with a mass of 5.486 into 10 to the power minus 4 with a mass number of 0 and charge of minus 1. For proton, 1.0073 is AMU, atomic mass unit, mass number 1 and charge plus 1. Similarly, other subatomic particles, mass, symbol, mass number and charge, they were also expressed and put it in this table. Now, why importance of electrons and electronic structure? Why there is a lot of importance is given for electrons and electronic structure? Atoms consist of nuclei and electrons. Only in the case of protium is the nucleus void of neutrons. Most chemistry is concerned with the behavior of electrons only. The number of electrons in an atom of an element controls the chemical properties of the element. If the chemical properties of elements are governed by the electrons of the atoms of the element, why do elements in the same group of the periodic table but with different total number of electrons behave in a similar manner? This question leads to the concept of electronic structure and a need to understand the organization of electrons in atoms. So these are the major discoveries in atomic structure. In 1896, A.H. Becquerel, he discovered radioactivity of uranium. 1897, J.J. Thomson showed electrons have negative charge with charge to mass ratio 1.76 into 10 to the power 11 C by kg, coulombs per kilogram. Millikan measured the electric charge as 1.60 into 10 to the power minus 9 coulomb. Therefore, mass of electron is equal to 9.11 into 10 to the power minus 31 kilogram. Rutherford established the nuclear model of the atom, a very small heavy nucleus surrounded by mostly empty space. In 1913, H.G.J. Moseley, he determined the nuclear charges by X-ray emission, establishing atomic numbers as more fundamental than atomic masses. We will study about Rutherford's atom model and how it failed. In 1911, Ernst Rutherford proposed that an atom consists of a positively charged nucleus around which electrons move in circular orbits. In a classical model of such an atom, the electrons obey Newton's law of motion, and Rutherford's proposals were flawed because the electrons would be attracted towards the nucleus and would plunge towards it. The orbits could not be maintained. Additionally, this classical picture can only describe completely the relative position and motions of the nucleus and the electrons in the hydrogen atom. In atoms with more than one electron, it is impossible to solve algebraically the equations describing their motion. Even for hydrogen, however, the Rutherford's description was not able to account for some experimentally observed spectroscopic properties. So these are the reasons why Rutherford's atom model got failed. So see the model where electrons are revolving around the metal, around the nucleus, but we know that the electrons would be attracted towards the nucleus and would plunge into the nucleus, and definitely then there won't be any existence of the electrons. Then Bohr atom model came. In 1913, Niels Bohr developed a quantized model for the atom. In the Bohr atom, electrons move in planetary-like orbits about the nucleus. So electrons move only through orbits. The basic assumption that made the Bohr atom different from previous model was the energy of an electron in a particular orbit remains constant and that only certain energies are allowed. So this is the major difference between Rutherford's atom model and Bohr atom model. Here, in Bohr atom model, the basic assumption that made the Bohr atom different from previous model was that the energy of an electron in a particular orbit remains constant and that only certain energies are allowed. By classical theory, an electron cannot move in circular orbit until there is a force holding it on this path. If there is no attractive force acting on the electron, it will escape from the orbit. Think what happens if using a ball tied on the end of a string in circle and then let go of the string. Same thing will happen. So in this figure, it shows an electron moving with a velocity v in a circular path about the fixed nucleus. Velocity is a vector quantity, and for any given point in the path of the electron, the velocity will have a direction tangential to the circle. In the Bohr atom, the outward force exerted on the electron as it tries to escape from the circular orbit is exactly balanced by the inward force of attraction between the negatively charged electrons and the positively charged nucleus. So, as per the Bohr atom model, the outward force exerted on the electron as it tries to escape from the circular orbit is exactly balanced by the inward force of attraction between the negatively charged electron and the positively charged nucleus. Thus, the electron can remain away from the nucleus. Bohr built into his atom model the idea that different orbits are possible. Different orbits are possible, and that the orbits could only be of certain energies. This was a very important advance in the development of atomic theory. By allowing the electrons to move only in particular orbits, Bohr had quantized his model. This model was successful in terms of being consistent with some atomic spectroscopic observations, but the Bohr atom fails for other reasons. We have considered the organization of electrons in an atom in terms of classical mechanics and classical quantum mechanics. In the late 19th century, an important failure of the classical approach was recognized, the so-called ultraviolet catastrophe. This failure led Max Planck to develop the idea of discrete energies for electromagnetic radiation. That means the energy is quantized. Equation shown below is the relationship between E and frequency nu. So between energy E and the frequency nu, the proportionality constant h is the Planck's constant. So we can write E is equal to h nu. Here the units of energy E are in joules, the frequency of nu are in per second or in hertz, and h is Planck's constant with a value of 6.626 into 10 to the power minus 34 joule second. So quantization is the packaging of a quantity into units of discrete size. Planck's model assumed that light was an electromagnetic wave. In 1905, Albert Einstein proposed that electromagnetic radiation could exhibit particle-like behavior. However, it became apparent that while electromagnetic radiation possessed some properties that were fully explicable in terms of classical particles, other properties could only be explained in terms of waves. These particle-like entities became known as photons, which has an energy of h nu. Now let us return to the electrons in an atom. In 1924, Louis de Broglie argued that if radiation could exhibit the properties of both particles and waves, something that defeats the laws of classical mechanics, then so too could electrons, and indeed so too could every moving particle. This phenomenon is known as wave-particle duality. So electrons also can behave like both particles and waves. The de Broglie relationship showed that a particle with a momentum mv, m mass and v velocity of the particle, has an associated wavelength lambda, and the relationship between the momentum and the lambda is lambda equal to h by mv, where h is Planck's constant. This equation combines the concept of classical momentum with the idea of wave-like properties, and so we have begun to move towards quantum mechanics and away from classical mechanics. Let us see what this means for the behavior of electrons in atoms. Quantization is the packaging of quantity into units of discrete size. This point you should remember. Next is Heisenberg uncertainty principle. For a particle with a relatively large mass, wave properties are unimportant and the position of the motion of the particle can be identified or defined and measured almost exactly. However, for an electron with a tiny mass, this is not the case. Treated in a classical sense, an electron can move along a defined path in the same way that a ball moves when it is thrown. However, once we give the electron wave-like properties, it becomes impossible to know exactly both the position and the momentum of the electron at the same instant in time. So it becomes impossible to know exactly both the position and the momentum of an object at the same instant in time. This is Heisenberg uncertainty principle, and the equation associated with this principle is delta x into delta p greater than or equal to h by 2, where delta x and delta p are uncertainty in position and momentum. We must now think of the electron in a new and different way and consider the probability of finding an electron in a given volume rather than trying to define its exact position and momentum. The probability of finding an electron at a given point in space is determined from the function psi square, where psi is the wave function. A wave function is a mathematical function which tells us in detail about the behavior of an electron wave. Now, we must look for ways of saying something about the values of psi and psi square, and this leads us to the Schrodinger wave equation. So the probability of finding an electron at a given point in space is determined from the function psi square, where psi is the wave function. One form of Schrodinger wave equation is given here, xi equal to E psi. When first looking at this equation, you might ask, can one divide the equation by psi and write h equal to E? This seems a reasonable question. But in order to answer it, and the answer is no, we need to understand what the various components of equation mean. Look first at the right hand side of the equation. We have already stated that psi is a wave function. E is the total energy associated with the wave function psi. The left hand side of equation represents a mathematical operation upon the function psi, and that function h, that operator is called Hamiltonian operator and represented using the letter h. Equation 1 can be expressed generally like operator working on a function equal to a scalar quantity into the original function. The equation is set up so that, having operated on the function in our case, the answer comes out in the form of a scalar quantity in the case of E, in our case it is E, multiplied by the same function, in our case psi. So one more time, the equation is set up that having operated on the function psi, the answer comes out in the form of a scalar quantity, here it is E, multiplied by the same function which is psi. For such relationship, the function is called an eigenfunction. So psi is an eigenfunction, and the scalar quantity is called eigenvalue. So E is an eigenvalue. Applied to equation 1, this means that psi is an eigenfunction and E is an eigenvalue, while h is the operator. Just as the name suggests, a mathematical operator performs a mathematical operation on a mathematical function. For example, differentiation is one type of mathematical operation, like d by dx instructs you to differentiate a variable with respect to x. The Hamiltonian operator is a differential operator and takes the form minus h square by 8 pi square m, dou square by dou x square, plus dou square by dou y square, plus dou square by dou z square, plus v of x, y, z, in which dou by dou x square, dou by dou y square, and dou by dou z square are partial differential, and v of x, y, z is a potential energy term. The complicated nature of h arises from the need to describe the position of the electron in a three-dimensional space. Why the term h or why h is more complicated in nature? Because it actually needs to describe the position of electron in three-dimensional space, which is difficult to mention or represent. It is difficult to grasp the physical meaning of Schrodinger equation. However, the aim is not to study this equation in detail, but merely to illustrate that the equation can set up for a given system and can be solved either exactly or approximately to give the value for psi and hence psi square. From the Schrodinger equation, we can find energy values that are associated with particular wave functions. The quantization of the energies is built into the mathematics of Schrodinger equation. A very important point to remember is that Schrodinger equation can only be solved exactly for two-body problem, that is, for a species that contains a nucleus and one electron. For an example, in hydrogen atom, one nucleus and one electron, helium ion, one nucleus and one electron, lithium 2 plus ion, one nucleus and one electron. These are all hydrogen-like species, and Schrodinger equation can be only solved for these kind of hydrogen-like species. The wave function is the solution of the Schrodinger equation and describes the behavior of electrons in the region of space of the atom called the atomic orbital. One more time, the wave function is a solution of Schrodinger equation and describe the behavior of the electron in the region in the space of an atom called atomic orbital. These results can be extended to give information about a molecular orbital in a molecular species. This result can be extended to get the information about molecular orbital if the species is a molecule. An atomic orbital is usually described in terms of three integral quantum numbers. You will study about quantum numbers in detail later. The principal quantum number n, which is a positive integer with values lying between the limits 1 and 7. For most chemical purposes, we are within the limit n equal to 1 to 7. Two further quantum numbers L and Ml may be derived. We will study this later. And a combination of these three quantum numbers define a unique orbital. So we require three quantum numbers, that is principal quantum number n, quantum number L, quantum number Ml. These three different or these combinations of these quantum numbers defines a unique orbital. Major points from this topic: a wave function psi is a mathematical function that contains a detailed information about the behavior of an electron. The region of space defined by such wave function is termed as an atomic orbital. Each atomic orbital may be uniquely defined by a set of three quantum numbers n, L, and Ml. So far, we have described the position of the electron by Cartesian coordinates, that is x, y, z, with the nucleus 0, 0, 0, 0, y, 0, and z, 0. It is very often convenient to use a different coordinate system which separates a radial distance coordinate r from the angular components theta and phi. These are called spherical polar coordinates. So see the figure here. The definition of polar coordinates are theta, phi for a point shown here in red. R is the radial coordinate and theta and phi are angular coordinates. Cartesian coordinate x, y, z are also shown in this figure. The point at the center of the diagram we have to consider it as the origin. We will not be concerned with the mathematical manipulations used to transform a set of Cartesian coordinates into spherical polar coordinates. We are not concerned about the mathematical manipulations used to convert the Cartesian coordinates into the spherical polar coordinates. However, it is useful to be able to define separate wave functions for the radial, that is radial wave function, radial, that is r, and angular, that theta and phi, components into psi, that is wave function. This is represented in equation which is given here, that is psi Cartesian xyz, the psi radial into psi angular. and that function we can rewrite into r of r a theta phi. So this is the radial part and this is angular part. So psi Cartesian can be now written as a combination of radial wave function part and spherical angular wave function part. So r of r into a of theta phi. Hence, the components should really be written as r of n r and a of l m theta and phi. In our class, we shall simplify these expressions. So instead of writing r and r, we will use r r. Instead of using a l m theta phi, we will use a theta phi for our convenience. The notation RR refers to the radial part of the wave function, and a theta phi refers to the angular part of the wave function. It follows that RR will give distance information, where a theta phi will give information about the space. So RR will give information about the distance and a theta phi will give information about the shape. The functions psi square, RR square, a theta, phi square. We will study in detail about these steps. The function psi square is proportional to the probability density of the electron at a point in space. That is the meaning of psi square, the function psi square. By considering the values of psi square at points in the volume of space about the nucleus, it is possible to define a surface boundary that encloses the region of space in which the probability of finding the electron is 95%. By doing this, we are effectively drawing out the boundaries of an atomic orbital. Remember that psi square may be described in terms of radial and angular components. We studied earlier RR square and a theta phi square. Remember also that these boundaries are only approximations. In principle, all orbitals are infinitely large. This is just for approximation. So the boundary of the orbital is just an approximation. In principle, all orbitals are infinitely large. We will take example the oneness atomic orbital. The lowest energy solution to the Schrodinger equation for the hydrogen atom leads to the oneness orbital. The oneness orbital is spherical in shape. It is spherically symmetric about the nucleus. We already studied those things in the earlier classes. If you are interested only in the probability of finding the electron as a function of distance from the nucleus, we can consider only the radial part of the wave function RR. So if our interest is to study to find the probability of finding an electron as a function of distance, we have to consider only the radial part of the wave function RR. Values of RR square are largest near to the nucleus and then become smaller as we move along a radius centered on the nucleus. So the maximum values RR will be getting very near to the nucleus, and the values of RR square will be decreasing when we are moving away from the nucleus. Since the chance of electron being far out from the nucleus is minutely small, we draw a boundary surface for the orbital so as to enclose 95% of the probability density of the total wave function psi square. So we find what is the 95%. We have to draw a boundary surface for the orbital so as to enclose 95% of the probability density of the total wave function psi square. And if you draw a graph where we are plotting RR square against a distance from the nucleus, we can see that the maximum RR square value, which is very near to the nucleus, and the value of RR square is decreasing when we are moving away from the nucleus, and we know that at a particular time the value becomes minutely small, not zero, minutely small. Now we have to draw if you are drawing a boundary surface around boundary surface around the nucleus where 95% of possibility for finding an electron, then we will get information about the distance of the electron from the nucleus, the most probable probability of finding the electrons. We know that when the distance leads to infinity, at that time the RR square will be reaching near to 0. So this is a plot of RR square as a function of distance r from the atomic nucleus. This plot reverses in case of a spherically symmetrical 1s orbital. This drawing is only for 1s orbital. Next is normalization. Wave functions are usually normalized with unity. This means that the probability of finding the electron somewhere in space is taken to the unity 1. So probability of finding electron somewhere in the space is 1. That means, in other words, the electron has to be somewhere. Mathematically, the normalization is represented by the equation integral psi square d tau. If you are integrating psi square with d tau, it's equal to 1. This indicates we are integrating over all space, that is d tau, and that of the total integral of psi square must be unity. Radial distribution function. Another way of representing information about the probability density is to plot a radial distribution function. The relationship between RR square and the radial distribution function is this. If you want to get radial distribution function, you have to substitute the RR square value in this equation, that is 4 pi r square RR square. The advantage of using this new function is that it represents the probability of finding the electron in a spherical shell of radius. You see the spherical shell of radius r and thickness dr, where r plus dr may be defined as v plus a small increment of radial distance shown in figure. A view in this is a view into a spherical shell of inner radius r centered on the nucleus and thickness dr, where dr is a very small increment of the radial distance r. Thus, instead of considering the probability of finding the electron as a function of distance from the nucleus as illustrated in this figure, we are now able to consider the complete region in space in which the electron resides. This figure shows the radial distribution function for the radial distribution function, not the RR square as the function, as 4 pi r square RR square, that is radial distribution function against the distance from the nucleus. If you draw the graph, then the nature of the graph will be looking like this. Notice that it is 0 at the nucleus. This contrasts with the situation of RR square, where the RR square value was at the highest at nucleus. But here if you draw, when you draw the graph 4 pi r square RR square, then we will be able to see that the value of 4 pi r square RR square is 0 at the nucleus. The difference arises from the dependence of the radial distribution function upon r at the nucleus, that is r is 0. So 4 pi r square RR square must be equal 0. So at nucleus r value is 0, so 4 pi r square will become 0. So the total value of 4 pi r square RR square will become 0. So 4 pi r square at the nucleus must be equal to 0. So 4 pi RR square describes 4 pi r square RR square describes the probability of finding the electron at a distance r from the nucleus. The maximum value of 4 pi r square RR square corresponds to the distance from the nucleus where there is the maximum probability of finding the electron. So radial distribution function, that is 4 pi r square RR square, It gives the probability of finding an electron in a spherical shell of radius r and thickness of dr. The radius r is measured from the nucleus.